Welcome. This video is going to talk about reaction rate laws and how you determine the order of a reaction rate law. So average reaction rate is just that. It's an average rate over time. But in reality, reactions always tend to slow as the concentration of reactant decreases over time. So the reaction rate is always going to be the fastest or the greatest at the very start of your reaction, and then it immediately begins to decrease until equilibrium is reached. That's why when you see reaction rate diagrammed, if you're looking in terms of the reactants, you're going to see this exponential graph as the reactant decreases. Or if you're looking at the rate in terms of product produced, the greatest amount is produced right at the beginning, and then it levels off until you reach this idea of equilibrium. So rate laws express the mathematical relationship between the rate of the chemical reaction and the concentration of the reactants. Okay, so if the rate and the reactants have a 1-to-1, if the concentration goes down by half and the rate decreases by half, we would say that's a 1-to-1 relationship. So we're going to look at these mathematical relationships, and they have to be determined experimentally. So in some of the examples here, I will be giving you data to evaluate, because that's the only way scientists can determine the mathematical relationship, is to actually do the experiment, change the concentrations, and measure the difference in the rate. So what the rate laws do is show or prove that reaction rate is directly proportional to the concentration of reactants, and different reactants have a different effect on the rate law. So reaction rate laws, if we look at the very simplest example, it would be just a one-step reaction, and in this case I made it as simple as possible. One reactant converts into one product, and your rate could be expressed as K times the concentration of A, where K is a specific rate constant which is specific for a temperature and unique for each reaction. So K can have a variety of units. It depends on how many reactants you have involved. In this form, the simplest form, would just be liters per mole per second. If you had two reactants, it often would be liters squared per mole squared per second. Or it could just be per second if things cancel out. It totally depends on the number of substances and any exponents that show up in your rate law. What is consistent is a larger value for K indicates a faster reaction, and changing temperature doesn't affect the rate law, but it will affect the value of K. And I noticed that got cut off on here. It does affect K, because remember, K is for a specific temperature. So first order reaction rate law, an example of this would be if we looked at the reaction of hydrogen peroxide decomposing into water and oxygen. The reaction rate has been experimentally found to be equal to K times the concentration of H2O2. And on the next slide, I have a graph, and you can see there's a linear relationship between the concentration of peroxide and the rate. So it's a 1-to-1 or linear relationship. So really we can think of the rate as the rate constant times the concentration of peroxide to the first power. But there's no need to write that one, since it has no effect on the numerical value. But that's why this would be known as a first order reaction rate. So another example here. So here's the graph I was talking about. Your hydrogen peroxide concentration, you notice it's increasing, and the rate of the reaction is also increasing. Or if you were looking at the hydrogen peroxide decreasing, you'd look from right to left, then the rate also decreases. So it's a linear relationship. They increase and decrease together. So what about other order reaction rate laws? In many reactions, the relationship between the reaction rate and the concentration isn't 1-to-1 or linear, but it's always proportional. So anytime you have more than one reactant involved, the order will be greater than 1. And if there's more than one step in the reaction or more than one activated complex, the order will also be greater than 1. So the overall reaction rate order is going to be the sum of orders for the individual reactants in the rate law. So if you can determine the order of the individual reactants, you can then put together your overall reaction rate and determine your overall reaction rate order. So the general rate law says if you have reactants A and B combining to form some products, or small a and small b are coefficients, then the rate should be equal to your specific rate constant times the concentration of A to the m power times the concentration of B to the n power, where m and n are going to be the reaction orders for each reactant, and these reaction orders or exponents have to be found experimentally. And finally, m and n will be equal to the coefficients A and B only if it's a single-step reaction. So how do we find it? Well, if we look at this example here where 2NO plus 2H2 yields N2 plus 2H2O, and we had experimental data that showed when NO is doubled, the reaction rate quadruples. Let me just underline that information. So if I've got 2 times NO, the rate becomes 4 times as much. But if H2 doubles, my rate simply doubles. So my reaction rate would be described as second order in NO and first order in H2, because when I double NO, it quadruples, or it's taken to the second power, whereas when I doubled H2, it was only taken to the first power, or only doubled. So my rate would be written as K, or my specific rate constant, times the concentration of NO squared times the concentration of H2 to the first, or I could just write it K concentration NO squared times the concentration of H2. My overall reaction rate order would be considered third order because I add up my 2 exponents, 2 and 1, and I come up with third order overall. So give the individual reaction rate orders for each substance and the overall reaction rate order if you're given a rate of K NO2 squared and Cl2 squared. Well, my individual reaction rate orders, it would be second order for NO2, since that's the exponent for NO2. It would also be second order for Cl2, since that's the exponent. And that means overall, it's a fourth order reaction rate. Here's another example for you to try. Write the rate law for the general reaction involving reactants A, B, and C if the reaction is in the second order in A, zero order in B, and first order in C. And then determine the overall order for this reaction. So go ahead and pause and see what you can come up here. So my rate would be K. You always have to include that constant. And I have the concentration of A, and since it's in second order, use the exponent 2. I have a concentration of B, and I'm told that's zero order. And a concentration of C is first order. So this rate would really simplify to K A squared times the concentration of C. Since B to the zero order is equal to 1 and C to the first order is equal to just the concentration of C. What's the overall order? Well, if I add up 2, 0, and 1, my overall order again is third. Here's one more for you to pause and try. How would the reaction rate change, assuming constant temperature, if the reaction is first order in reactant A and A is cut in half, or if the reaction is second order in reactant B and B is triple? So if we look at the first example here, if A is cut in half and it's first order, then that means it's got a 1-to-1 relationship. If I have 1/2 times my concentration of reactant A, I guess I don't need to write reactant. If I have 1/2 times the concentration of A, and that's going to be taken to the first power, then I would expect my rate to be cut in half. But with B, if B is in the second order and I have 3 times the concentration of B, and I know it's second order, then when I triple B, that means I'm going to take 3 to the second, or my rate should increase 9 times. And that's an intro to reaction rate orders.